When you picture yourself doing absolutely nothing, like say you're just lying perfectly still on the couch, right? Staring at the ceiling, feeling completely at peace, you probably imagine your body is at rest too.
Right, yeah, like a parked car with the engine switched off.
Exactly, just sitting silently in the driveway. But based on the physiology texts and medical histories we're looking at today, that is a massive illusion.
Oh, absolutely. It's a very peaceful image, but beneath that calm surface, your biology is essentially, well, is furiously bailing water out of a sinking boat, like every single second, just to keep you from drowning in chaos.
Okay, let's unpack this. Because of that imagery totally shifted how I view my own body. We think we're at rest, but we're actually in this state of relentless, high-stakes biological warfare against the environment. And that really is the mission of today's deep dive.
Yeah, we aren't just learning a biology term today. We really want to help you understand this invisible circuitry that keeps you alive.
Right. In a world that is constantly, trying to change your internal environment, it's this vital concept called homeostasis.
Right. It's the reason your blood sugar doesn't just spike into a fatal coma every time you eat, a candy bar.
Yeah.
Or why your core temperature doesn't instantly match the freezing air the second you step outside in winter.
Yeah. And the word itself is interesting because, well, the Greek roots are actually a bit of a trap. Homeo meaning similar or steady, and stasis meaning standing. But if you think of it as standing still, you're missing the entire point.
You're missing the magic of the system, yeah, because standing still implies it's passive.
Right. Like a rock sitting on a lawn.
Exactly the opposite.
Mhm.
To really appreciate what your body is doing right now, we need to travel back to mid-19th century Paris.
Okay, I love a good history detour.
Right. So we're looking at a physiologist named Claude Bernard. At the time, medicine was still grappling with how the body actually functioned, and Bernard proposed something pretty radical.
Well,
He suggested that all of the complex, wildly different organs in an animal, the lungs, the kidneys, the heart, they all exist for one singular unified purpose,
Mhm.
and that is to maintain constant conditions in what he called the milieu intérieur.
the internal environment.
Exactly.
So we're talking about the blood, the plasma, the fluids that are just bathing our cells.
Yes. And Bernard realized this stability wasn't just some, happy accident. He actually proved it by looking at the liver in the 1850s.
Right, the liver glycogen stuff.
Yeah. He discovered that the liver actively produces and stores a complex sugar called glycogen.
Mm.
He mapped out how if you eat a massive meal, the liver doesn't just let that sugar flood your blood, it actively pulls it out and tucks it away.
And then later, if you skip a meal,
Right. Your blood sugar drops,
Mhm.
and the liver just unpacks that glycogen and releases it back into the bloodstream to buffer the system.
So he was the first to really see that the body is actively defending its baseline against a fluctuating outside world. But the word homeostasis didn't exist yet, did it?
No. It actually took another 60 years for the concept to get its formal name and its framework. Which brings us to Walter Cannon.
The Harvard guy, right, in
Yeah.
the 1920s.
That's him. Brilliant researcher. Cannon was studying the autonomic nervous system, but his defining insights came from observing soldiers going into shock on the battlefields of World War I.
Oh, wait, he's the one who coined the phrase fight or flight, isn't he?
He is, yeah. And in those medical tents, Cannon watched bodies that had suffered massive trauma, desperately pulling blood away from the extremities to protect the core organs.
Just fighting to keep the core alive.
Yeah, he saw how fiercely, almost violently, the body's systems cooperated to defend blood pressure and core temperature, even as a soldier was, bleeding out.
Wow.
He realized Bernard's internal environment needed a really rigorous scientific framework. So in 1926, he introduced the term homeostasis.
And what I find so compelling about this era of medicine is the philosophical battle they were fighting. Because people at the time really wanted to believe in something called vitalism.
Oh yeah, the magical life force.
Right. It's this idea that living things survive because of some mystical, unquantifiable energy.
It's a very comforting, almost romantic notion, really.
Yeah.
The belief that you stay warm and breathing just because this magic energy keeps living things humming along.
But Cannon and Bernard were basically looking at the plumbing. They were
I
saying,
think-
no, it's not magic, it's mechanics.
Stability in an ever-changing environment doesn't just happen magically. It requires dedicated physical regulatory mechanisms.
Which is an incredibly empowering shift in perspective, if you think about it. You are kept alive by intricate physical circuitry.
Absolutely.
Let me throw an analogy at you from the sources that really help this click for me.
Go for it.
So we tend to think of this steady state like a perfectly insulated, sealed room that just passively sits at like 68 degrees.
Right, perfectly calm.
Yeah. But it's actually much closer to a terribly insulated shack in the middle of a screaming blizzard. And inside that shack, a thermostat is desperately cycling a massive furnace on and off over and over, roaring to life just to fight off the freezing cold outside.
Yeah, just to hold the temperature roughly around 68 degrees.
Exactly.
That captures the dynamic perfectly.
Right.
It is a moving average, it's constantly oscillating around a set point, never truly resting. And because you are fighting a blizzard, that furnace requires immense amounts of fuel.
Right. And this is the part that completely blew my mind. Wait, so even if you are just lying on the couch doing absolutely nothing, your body is burning massive amounts of metabolic energy just to maintain a neutral baseline.
A staggering amount, yeah.
Yeah.
To give you a concrete sense of this, let's look at one microscopic, incredibly busy mechanism, the sodium-potassium pump.
Okay.
This is a tiny molecular machine embedded in the membrane of your cells. Its entire job is to maintain ion gradients. It constantly bails sodium out of the cell and pumps potassium in.
Like piling water behind a dam.
Exactly like that. It creates an electrical charge across the cell membrane.
And I assume that electrical charge is pretty important.
Well, it is the absolute foundation of your nervous system.
Yeah.
Every single time a neuron fires, every thought you have, every muscle you twitch, those ions flood across the membrane to create an electrical spark.
Okay.
And immediately, those millions of tiny pumps have to grab the ions and shove them back into place to reset the gradient for the next spark.
So they are just running nonstop.
Continuously. In fact, biologists estimate that this one tiny mechanism, just the sodium-potassium pump alone, consumes somewhere between 20 to 40% of your body's entire resting metabolic energy.
Wait, really? Up to 40% of the calories I burn at rest are just going toward cellular water bailing.
Basically, yes. The illusion of doing nothing is just that, an illusion. Maintaining homeostasis is one of the largest continuous energy expenditures of simply being alive.
Okay, if it takes all this energy, and it's built on mechanical circuitry rather than magic, I really want to look under the hood here. How does this circuitry actually operate in the bodies of everyone listening right now?
So at its most fundamental level, almost every homeostatic system runs on what we call a negative feedback loop.
A negative feedback loop.
Right. Think of it like a four-part relay race.
Mhm.
First, you have the variable.
Like the thing being regulated.
Exactly. Blood pressure, temperature, oxygen levels. Second, you have the receptor, or the sensor, which is constantly monitoring that variable.
Like the thermometer in the blizzard check.
Precisely. Third, that sensor reports to the control center. The control center compares the current state to the target range, the set point, and decides if action is needed.
Makes sense.
And finally, the control center sends orders to the fourth component, the effector. The effector is the muscle, organ, or gland that physically produces a response to correct the deviation.
So variable, sensor, control center, effector.
You got it.
Let's put this into a real-world context, because I think we've all experienced the lag in this system. Say you're sitting on the floor for a long time reading a book and the doorbell rings. You jump up really fast, and for a split second, the room spins and your vision goes black. What exactly is happening in the circuitry there?
Yeah. So you are experiencing a momentary drop in blood pressure called orthostatic hypotension. Gravity has literally pulled the blood down into your legs, which means less blood and therefore less oxygen is making it up to your brain.
But I don't faint. Usually, anyway, my body catches it.
Hey, because of the loop. In the walls of your carotid artery in your neck and in your aortic arch near your heart, you have these specialized stretch sensors called baroreceptors.
Just sensors.
Yeah, they physically feel how much your blood vessels are stretching, which is basically a proxy for pressure. When you jump up and the blood drops, those vessels shrink. The baroreceptors immediately sense the lack of stretch.
And they send the alarm to the control center.
Yes, up to a part of your brainstem called the medulla oblongata. The medulla sees the pressure drop and fires signals down your sympathetic nervous system to the effectors.
To fix the pressure.
Right. It tells your heart rate to spike, and it tells your blood vessels to constrict, clamping down to force the blood back up against gravity.
Oh.
Within seconds, the pressure is restored, the dizziness fades, and you answer the door.
That is just incredible. The machinery is just running silently in the background. What about temperature? Because thermoregulation has to be one of the most obvious ones we experience daily.
Oh, it's a beautifully elegant loop. Your brain has a region called the hypothalamus, which acts as the control center for temperature. Its set point is roughly 37 degrees Celsius, or 98.6 Fahrenheit.
Okay.
If you go for a run in the hot sun, thermoreceptors in your skin and deep in your core send frantic signals to the hypothalamus that the variable is rising.
So what are the effectors in that scenario? How does it actually cool me down?
The hypothalamus triggers two main effectors. First, it activates your sweat glands, pushing water onto your skin so that when it evaporates, it pulls heat away with it.
Right, basic evaporation.
Second, it causes the blood vessels near the surface of your skin to dilate, to open up really wide.
Is that why my face gets incredibly flushed and red when I work out?
That's exactly why. Your body is pumping hot blood from your core out to the surface of your skin so the heat can just radiate off into the cooler air.
That makes so much sense.
Now, if you step into a freezing room, the exact opposite happens. The hypothalamus slams those surface blood vessels shut, vasoconstriction, pulling the blood deep into your core to protect your vital organs.
Which is why your fingers and toes go numb first in the cold.
Exactly.
Yeah.
If that's not enough to stop the temperature drop, the hypothalamus triggers a new effector, your skeletal muscles. It commands them to rapidly, involuntarily contract. We call it shivering.
And shivering generates heat.
Yes. The movement doesn't actually accomplish any physical work, but the friction and the metabolic breakdown of energy generate heat as a byproduct.
It's just forcing the furnace to burn fuel to warm the shack. Now, I want to clarify one thing before we move on. We keep using the phrase negative feedback loop, where the body counteracts or reverses the stimulus. You get hot, it makes you cool. Your blood pressure drops, it pushes it up.
Right.
Does the body ever use positive feedback?
It does, but it is extremely rare, and for good reason. Positive feedback doesn't stabilize a system, it amplifies it. It pushes the variable further and further away from the baseline.
Oh, I see.
You only want a positive feedback loop for self-terminating events that need to reach a rapid, explosive endpoint.
Give me an example of when I would want my body to intentionally spiral out of balance like that.
Blood clotting is a great example. If you get a severe cut, you don't want a slow, gentle balancing act to restore your skin. You want an immediate, aggressive response.
You want to plug the hole.
Right. So injured tissue releases chemicals that attract platelets. Those platelets release more chemicals that attract even more platelets, building in this avalanche until the hole is plugged.
Are there any other examples?
Childbirth is another classic one. Contractions trigger the release of oxytocin, which triggers stronger contractions, looping and amplifying until the baby's born. But for day-to-day survival, positive feedback is too dangerous. We rely on the steady seesaw of negative feedback.
Here's where it gets really interesting, though. Understanding how perfect those negative feedback loops are is fascinating, but we truly see their power and their terrifying limits when they break down.
Oh, absolutely. The breakdowns can be devastating.
A tragic example of this from the sources is a thermoregulation failure. In August 2001, an offensive lineman for the Minnesota Vikings named Corey Stringer died of heat stroke during a grueling training camp practice. Reports indicated his core body temperature reached roughly 108 degrees Fahrenheit.
42.2 degrees Celsius. That represents a catastrophic systemic failure of homeostasis. When you combine brutal external heat, high humidity, and the massive internal heat generated by a 300-pound athlete exerting maximum physical effort.
It's just too much.
Yeah, you can exceed the body's physical capacity to cool itself. The sweat doesn't evaporate fast enough, the vasodilation isn't enough, the temperature just keeps climbing.
But why is 108 degrees fatal? I think a lot of people might wonder, okay, you're really hot, but why does it actually kill you? I heard an analogy once about cooking an egg white.
That is the perfect way to understand it, actually. Your body runs on proteins and enzymes, and their function is entirely dependent on their physical shape. They fit together like microscopic locks and keys to trigger chemical reactions.
Okay, so shape is everything.
Right. When your temperature hits 108 degrees, the thermal energy is so intense that it breaks the delicate bonds holding those proteins in their specific shapes. They warp and unfold.
Like an egg white turning from clear fluid into solid white rubber when it hits the frying pan. It denatures.
Yes. And once those enzymes change shape, the keys no longer fit the locks. The chemical reactions that power your cells simply stop. At that temperature, you aren't just overheating, your biochemistry is unraveling, leading to rapid, irreversible organ failure.
It shows how incredibly narrow our survivable window really is.
It really does.
And we see a similar devastation when the machinery itself is fundamentally broken rather than just overwhelmed, like with blood glucose regulation. The story of Leonard Thompson in 1922 is profoundly moving. He was a 14-year-old boy in Toronto, and he was dying of type 1 diabetes.
Right. To understand what was happening to Leonard, we have to look at the pancreas. Normally, when you eat a meal, glucose levels in your blood rise. Beta cells in the pancreas detect this and release insulin.
And insulin is basically the key, right?
Exactly. It acts as a key to unlock your muscles and liver, telling them to pull the sugar out of the blood and store it. But in type 1 diabetes, the immune system makes a fatal error. It attacks and destroys those beta cells.
So the control center for the too high side of the loop is just eradicated.
Precisely. Without insulin, the body doesn't know how to store the glucose. The sugar builds up to thick, toxic levels in the blood, but because the cells can't access it, the body literally starves to death while drowning in fuel.
That is awful.
Before 1922, this was a slow, agonizing, near-certain death sentence.
But Leonard Thompson became the very first patient successfully treated with external insulin, right? Prepared by the researchers Frederick Banting and Charles Bess.
They did. They realized that if the internal loop was broken, they could manually close it from the outside. By injecting insulin derived from animals, they artificially provided the missing messenger. Leonard, who was slipping into a coma, woke up. His blood sugar dropped. It remains one of the greatest, most visceral triumphs in medical history, manually hijacking a homeostatic loop to save a life.
But there's a flip side to this that I found truly unsettling in the medical histories. Sometimes homeostasis fails not because it's overwhelmed or broken, but because it's working too well in the wrong context.
Ah, yes. You're talking about the evolutionary mismatches.
Yes, the 2002 Boston Marathon case study published in the New England Journal of Medicine.
This is a fascinating and tragic scenario. When you engage in intense endurance exercise, your brain's posterior pituitary gland releases something called antidiuretic hormone, or ADH.
Okay, what does ADH do?
Your evolutionary programming assumes that if you're running for hours, you are probably hunting or fleeing, and you might not have access to water for a long time. So ADH tells your kidneys to conserve water at all costs. Do not let any water out through urine.
Which makes perfect sense if you're, running across the savannah. But at a modern marathon, runners are constantly passing water stations. The culture screams at them to hydrate, so they are chugging massive amounts of water while they run.
And here's where the ancient circuitry backfires. The ADH is still screaming at the kidneys, do not let a drop of water go. So all that water they are drinking stays trapped in the blood.
Oh, no.
When you add that much water to a closed system, it dangerously dilutes the concentration of sodium in the blood.
This causes a condition called hyponatremia, right?
Yes, and because the blood is now so watery, osmosis forces that excess fluid into the body cells, trying to balance the concentration. The cells swell up like water balloons. Now, if a muscle cell swells, it hurts, but you survive.
Not the brain.
Exactly. If your brain cells swell, they have nowhere to go inside the rigid human skull.
The New England Journal study found that roughly 13% of the runners tested at that marathon had some degree of hyponatremia. And tragically, a young woman named Cynthia Lucero actually collapsed and died from hyponatremic encephalopathy. Her brain swelled due to water intoxication.
It is a sobering reminder that our internal regulatory reflexes are deeply stubborn. They evolved for prehistoric conditions. When you place entirely unnatural modern demands on them, the very mechanism designed to save you can become lethal.
So what does this all mean? Are we just trapped by these static numbers? Are we stuck with a rigid thermostat that blindly follows an ancient rule like conserve water even when it kills us?
Well, for a long time, the classical view was that set points were static. A deviation happens, the body reacts and pushes it back. But in the late 1980s, researchers like Peter Sterling, Joseph Iyer, and later Bruce McEwen realized that the classical view was incomplete. They introduced a concept called allostasis.
Allostasis, meaning stability through change.
Exactly. They argued that physiological set points aren't rigid, fixed numbers hanging on a wall. They shift predictively in anticipation of demand.
Predictively? How so?
Think about waking up in the morning. Your blood pressure doesn't just wait for you to stand out of bed, drop, and then frantically play catch-up. Driven by a daily rhythm of cortisol, your blood pressure actively rises before you open your eyes. Your body anticipates that you will need more blood flow soon and shifts the baseline.
Oh, that makes sense. Or like when you step onto a treadmill at the gym, before you even start running, just the anticipation causes your heart rate to jump. Your brain knows the metabolic demand is coming and proactively moves the thermostat.
What's fascinating here is how it completely reframes things we used to consider broken homeostasis. And the ultimate example of this is a fever.
Okay, this completely blew my mind. For a long time, folk wisdom, and even a lot of medical wisdom, treated a fever as a malfunction. We thought the body's thermostat was broken because the infection was damaging the machinery.
Right. But a fever is not a malfunction. It is a deliberate, highly regulated resetting of the set point. When you get a bacterial or viral infection, your immune cells release signaling molecules called pyrogens.
Pyrogens.
Yeah, these pyrogens travel to the hypothalamus and intentionally crank the thermostat up, let's say from 98.6 to 102 degrees.
Nicholas Mersovsky coined a term for this in sources, rheostasis, the regulated changing of a set point. So my body actually wants to be at 102.
Yes, the hypothalamus establishes 102 as the new normal. And this is why you feel freezing cold when a fever is coming on.
Because I'm at 98.
Right, your physical body is currently at 98.6, but the control center says we need to be at 102. So you start violently shivering, your blood vessels constrict, you get goosebumps, and you huddle under 3 blankets.
Wow.
Your homeostatic machinery is working flawlessly, actively driving your temperature up to hit that new target, because the heat creates a hostile environment for the pathogen and supercharges your immune cells.
It's not a broken loop. It's a hijacked loop, executing a new temporary master plan.
Precisely.
When you really zoom out and look at all of this, it isn't just biology trivia. This is the foundation of how we interface with our own health. Every piece of everyday folk advice, stay hydrated, don't overexert yourself in the heat, eat a snack so your blood sugar doesn't crash, you aren't really fixing anything. You are just providing manual external support for your biological feedback loops before they max out.
And modern medicine is essentially the science of diagnosing those loops. Hypertension is a failure of the blood pressure loop. Kidney disease is a failure of the fluid and pH loops. Most pharmaceuticals aren't magic cures. They are tiny, precise chemical nudges designed to push a struggling feedback loop back into its functional range.
It's incredible how delicate the balance is.
It is, and this raises an important question, actually, one that builds on Bruce McEwen's work.
Oh,
He developed this concept called allostatic load. Basically, it's the cumulative wear and tear of chronic stress constantly triggering these anticipatory systems.
wear and tear from stress.
Yeah. If our bodies are designed to predictively shift our baselines in response to anticipated demands, like raising blood pressure for an impending threat, what happens when the threat never leaves?
Oh, wow.
How is the constant low-level chronic stress of modern life permanently rewriting the internal set points we were born with? Are our bodies getting stuck in an elevated baseline that's slowly wearing out the machinery?
That is definitely something for everyone to mull over. So
Yeah.
the next time you find yourself lying perfectly still on the couch, staring at the ceiling, thinking you're doing absolutely nothing, take a second to appreciate the quiet, frantic, metabolic miracle bailing water out of the boat just to keep you afloat. Thanks for joining us on this deep dive. We'll catch you next time.